Welcome. Let me introduce myself. Let me introduce you to the talk, Bringing Order to the Chaos. My name is Paulo Lopes, and I'm a principal software engineer at Red Hat, where I work, among other things, as Eclipse Vertex core developer. I consider myself a polyglot, and I'm fluent in many languages. I speak English, I speak Portuguese, I speak Java, I speak JavaScript. And I've been working on many industries. I've worked on the game industry before. I work in software navigation. I've been a software architect. And right now, at Red Hat, I'm an open source contributor. But this talk is not about me, so enough about me. The agenda for my talk can be resumed as this very simple Latin expression. Probably everyone has seen it before. It means to err is human. And knowing that software is built by people like you and me, and because we are humans, by inference, we know that there will be bugs. And bugs in software are very, very expensive. Just a bit of divergence, just to give some idea of these values. I just Googled and I went on Wikipedia for a couple of high-profile software bugs. And these are just a few that I made a selection. There's no real importance here, but it's just for you to have an idea. So in 1987, I need to look at the notes because I don't know this by heart, the Wall Street market crashed, and it was known as the Black Monday. The reason why it crashed is very software related. So basically, what happened was that the SEC, it's an institution in the United States, was investigating some trading companies that were doing some trading using inside knowledge, which is illegal. And because of that, all the investors of other stock companies starting selling the stocks because they know that the market, the value of the stocks will be low. What happens here is that because of all these sell orders weren't expected on the system, too many transactions were requested on the stock market, and the software there crashed. And the cost was that because of this, they lost 22.6% of their value, which means more or less, give or take, $500 billion per day that the system was down. And it was down for several days. Another example was the Pentium. Maybe you guys remember, if you are not too old like me, when the first Pentium came out from Intel, it had a division bug. Basically, the error was caused because inside the processor there are some division tables, and someone forgot to add a couple of lines on those tables. Some lines were missing. So in some cases, the values would not, the division values would not be valid. And this cost Intel $475 million. And everyone knows about the year 2000 problem because we are storing dates with 2 digits instead of 4. So 1900 or 2000 would mean the same. Lots of software had to be fixed because of this decision made in the past, assuming, well, by 2000 everyone will be running something else. And that wasn't true. And that cost, again, $500 million. If you guys want to see like the sources, the presentation itself, I'll make it online, and all this information as links to the source, so you can check the numbers if you're interested. And finally, this year, we have the meltdown on Spectre bugs again on chips. Again, software-related problem, and we don't even know how much it's going to cost. What I want to tell you is, no matter what, fail is inevitable. Sooner or later, things will come apart and fall. So there's no way that you can always prevent all the problems, all the issues that can happen or all your weaknesses in your system. So, in order to fight this, a big company called Netflix had a dedicated engineering team to try to minimize the issues with their downtime, because, well, if there's downtime, Netflix users will be upset because they cannot see their shows. So this engineering team coined the term chaos engineering. In order to explain what chaos engineering is, I looked around, and my favorite description comes from the Forbes magazine. And I'm going to read it because it's a long description. So Forbes magazine describes chaos engineering as: think of a vaccine or a flu shot. While seemingly counterintuitive, you inject yourself with something harmful in order to prevent a future issue. The same technique applies to complex systems on the cloud as well. So chaos engineering is about hurting yourself on purpose, so when it really happens again, you are ready. So to put it in a more formal description, you can think of chaos engineering as a discipline of experimenting on a distributed system in order to build confidence in the system capability to withstand turbulent conditions in production. I highlighted like the most important parts in my opinion, and I even put on bold the word production. I don't know if you see it, but it's a bit thicker. So everyone will think chaos engineering is a crazy idea. You are going to test stuff on production. No one wants to test things on production. But the important thing is to know is that development, staging, and production do not behave the same way. So chaos engineering, what's chaos engineering? I can define chaos engineering in 5 principles. So principle number 1, you should build an hypothesis around a steady behavior. So you need to create tests on your system to know that your system is working correctly. So you need metrics measured to know how it behaves. Principle number 2, we need to vary real-world events. Because when you're just testing on development and on staging, you might think of that your system can suffer from specific errors, but those errors are not necessarily what happens on production. Say that you assume that your biggest weaknesses are that you're going to have a big burst of clients connecting to your system, but on real life, what happens is because you are on the cloud and the network goes down and you lose the connection to the database and your application doesn't work. Third principle, you need to run these experiments in production. And this is very important because if your system can accept these tests to be run in production, then it means that production is ready to withstand problems. The fourth principle is that, of course, you're going to run tests, then you need to automate. You're going to automate these experiments to run continuously. You have a background job that keeps running these tests. So because they are constantly running, then it gives you the guarantee and assures you that your system will withstand. And finally, because as I said, there is no way you're going to solve all your problems, you need to learn how to minimize the blast radius. If something goes wrong, what can you do to minimize its impact? If a database goes down, what can you do to mitigate the issue? Have a backup database as a solution. Have a copy of an old database with a couple of hours delay put in place so your systems can still do certain parts of the work. So in order to explain this and demo these ideas, I decided to build a simple application. And I decided to build a pass, because everyone loves pass these days. And my pass, basically, it's a Pong as a service. And I decided to describe my Pong as an application made of 2 components. There's a web client that allows you to run in your browser or your mobile, and there's a AI, because AI is trendy, right? A component that will run on the server side to control all the opponent pedals. So as you can imagine, this client-server application has a mission-critical service, which is the AI part, so to say, because if it doesn't work, then the opponent pedal doesn't move. It's like stays there. So in order to give this like a small description, I describe my project as Pong as a service is a highly available AI-based Pong application that computes in real time. The computer moves using a web service that scales to any number of users. And I underscore a couple of keywords on this description. Highly available, real time, and scales. Why did I do this? I did this on purpose, because if I go on Google or DuckDuckGo, whatever, and I look up for these words like responsive, resilient, and elastic, you will see that you end up with a link to the Reactive Manifesto. And the Reactive Manifesto is a manifesto that describes reactive systems. And reactive systems, that you probably already have heard, because it's nothing really new, can be described as this diagram that you see now on the screen. So what they say is that if you implement a message-driven architecture, then your application becomes elastic and resilient. And this is good, because in case there are errors, your application can self-heal, because it can be resilient to some errors. And if there's too much load, it can scale because it's elastic. And on top of that, it will give you a responsive application to your users, because no one likes to wait, for example. So my hypothesis is that if I build my Pong as a service, as a reactive system, it shall be responsive, delivering a consistent quality of service. It will be resilient, so it stays responsive in the face of a failure. And it will be elastic, so the system stays responsive under a varying workload. So knowing having this knowledge, you can quickly go look on Google or your favorite search engine for frameworks that would help you build such applications. And I did a quick summary on the table, and I have this. So basically, I just look up. There are way more. I just picked these four. You can think of building your application using Spring 5, Node.js, Vertex, or Akka. And you should be aware that they all are responsive, because they all implement reactive pattern. So all their CPUs will be maximized to use all the capacity on your hardware, but not all of them implement a reactive system, because a reactive system, as you saw from the previous diagram, is message-driven, resilient, and elastic. So from this list, I had to choose one, and as I said in the beginning, I am a core developer of the Eclipse Vertex project. So I will use Vertex because that's where I have more knowledge, but nothing here forbids you to use Akka or something else. It's just that my personal preference goes with Vertex. So I start implementing my application, and I'll show you here parts of the code. So I have here a couple of slides. So to keep this demo simple, this is my AI. And as you can see, I even put a smiley, because there's no AI, just a couple of if statements. You can later on read the full source code. It's already on GitHub on this URL if you're interested. And I'll share with you guys later on Twitter also. So basically, I define my handler for my AI. So basically, what I'm going to do, I'm going to wait for messages to my pass AI. And when a message arrives, I will look where the ball is, where the pedal is, and then generate an impulse to the pedal to go either left or right with a specific speed. So it tries to play against you. So this is very simple. So the second part, to complete my application is that I need to set up a server for this. So again, I'm using Vertex. I create a router, which is an object that will allow you to map HTTP requests to specific paths. So, and then I set up my first item from the chaos engineering thing. So I need to monitor. I need to know if my system lives. So I add a liveness probe. So I keep checking if my application is running. And then I add a readiness probe to see if my application is already started. In this case, they pretty much behave the same because it's a very simple application. But in a real-life scenario, your readiness probe would probably need to check if the database connections are open and ready. Can you do queries? Other third-party services are up. Other microservices, do you know where they are? Do you already discover them? And so forth. But this is to keep it simple in the demo. That's just simple as this. And then I create a event bus bridge. So the event bus is a concept within Vertex that allows you to send messages, because it's message-driven, between components. And these components can be either processes of the application or even the browsers. So by setting up this event bus bridge, I allow my browser to send messages to my application as if it was like a part of the same cluster. And finally, I just serve some static HTTP resources, such as some JavaScript, CSS, HTML, and I start an HTTP server to serve this all up. So you might think, what was wrong with the 2 slides that you just saw before? I just say, if you really paid attention, I have on the file names, I had like 1 of 3, 2 of 3, and my application is complete. So what I want to tell you is that you always need to think of a plan B. And my plan B is that I have again my AI implementation, but now implemented in Node.js. And this Node.js application can interact with my Vertex application because it's a reactive system. Vertex is a reactive system. It uses a message-driven architecture. As long as I can generate messages from any other platform, I can integrate it with my application. So my plan B is that I can always have a backup in case my JVM goes down, or in case there is a CVE that affects my production on a JVM, or my application relies on a library that is affected by a CVE that can be dangerous, like just happened with Apache structs a few months ago. If you know what I'm talking about. So in this case, having a different platform gives my developers some leverage to try to fix the problem that they are facing without the pressure that they need to shut down everything. So if you look for to make your application more resilient, you really should think of reactive systems. So I've been talking about real-world events. So I have here a small list of these events, and these events are inspired from the list of bugs that I presented in the beginning of the presentation. So these real-world events could be software bugs, because, well, every software will have a bug. Probably not now, but wait a couple of years and someone will find something. It could be a DDoS. And DDoS are kind of interesting kind of real-world events. You can be DDoS because someone doesn't like your company or your product and wants to put it down because they just want to make some point. Or you could even DDoS yourself. For example, when you build an application that you thought, well, I'm going to have around 50,000 users, and suddenly it becomes #1 on the App Store, and everyone now downloads the application. And instead of 50,000 users, you get like 1 million. And you never thought you would have that amount of users. So you DDoS yourself because you became popular. Other issues is the one I just talked in the beginning, network outages. Like network goes down, you lose the connection to your databases, to your external microservices. So once your network is down, then how do you recover? How do you handle it? And the last one, which I listed here, it's trivial, like a server crash. And this can happen for any reason, because you run out of memory, because there's a memory leak, because there was a bug in the code that run into a undefined state, because there's a bug in a library that you depend on. It can be anything, because someone tripped on a wire, a power cord, or because you are on the cloud and Amazon needs to roll update all their VMs because of Spectre and Meltdown. Can be anything. So, in order to do my demo, I need to create my fake production environment. And for this, I will use Openshift. So what is Openshift? This is just a personal choice, it's just to demo. So Openshift is a distribution of Kubernetes optimized for continuous application development and multi-tenant deployment. Openshift adds developer and operation-centric tools on top of Kubernetes to enable rapid application development. So if I would now go to my terminal, I would start my OpenShift cluster. And what OpenShift does is that it gives you a nice UI that you can interact with the application. And if you're really into it, then it even allows you to create like hybrid clouds, that part of your cloud is on Azure, AWS, and other part is on your local environment. So my OpenShift development environment is up, so I can quickly go on the browser. So I need to go here and do, okay. I have some, I think I put the right link. And of course there's no internet, so this will, connection is not secure, yes. Add exception. Really cannot see. Okay, so I have my developer. It's very secure. So my project is running. There's nothing there. So you can see there's nothing. So I can just go here and deploy my application. Because as I said, Vertex is JVM based. I use Maven, but you don't need to use Maven. You could just do whatever you prefer. So that's too many columns there. Too many columns. Fabric 8. Deploy. So this is like the typical Maven working, as you can see. So this is building and deploying, and now building on the. Can I close this? F11. And just close this window. So basically, what I run is OC cluster up to start OpenShift, and then I run Maven clean fabricate deploy. And well, it succeeded. So if I go here, you see that my application has been deployed and it's now starting. There's one pod. So my application is running, and I could try to test it. And if I test it, you see my Pong application here running. So a very simple Pong. So everything is running normal. So let me just put it on this side. A bit of a So as you can see, like the AI part is running, and if I want, I can go back here and go to let me see, a node, and I can do npm start. Well, I cannot. I need to. Download all the internet, of course. That's actually, it was not that bad. and I just put some logging to see that messages are being processed on the node side. So like my backup plan is also running, and now I can quickly go back to the presentation. So my application is running, and I need to talk about tooling. And now, for some reason, I lost my notes, but it doesn't matter because I know what I'm talking. There are two tools that you can use. Well, there are more tools, but the most popular tool that you can use to test your application is Chaos Monkey. And Chaos Monkey was built by Netflix, and it was built to fix Netflix issues. So it assumes that your application is deployed on AWS, it's deployed across several zones, and let's be honest here, my Pong application is not Netflix. It doesn't need such things so complex, and if I would test it on AWS, it means I would have to have a credit card ready, spend lots of money. So there's an alternative, and this alternative is called, there's something wrong with the slides. And the alternative is this. I'm terrible, sorry for this. The alternative is Pumbaa. And Pumbaa is an kind of a poor man version of Chaos Monkey, and it's named after the monkey on Lion King. And what Pumbaa does is it works with Docker containers. And as I said, I was using OpenShift because OpenShift builds on top of Kubernetes. Kubernetes builds on top of Docker containers. So it's like a perfect match. I can run everything in a very small environment, either be my local cluster or even my laptop for demo purposes. So Pumbaa does all I need. But Pumbaa itself doesn't do much because it only works with affecting the network and killing containers. So there are a couple of two more things. I'm going to use Work, WRK, which is a very popular tool to do load testing. And I'm going to use TC, which is part of the Linux kernel. TC is a tool that was developed by the kernel developers to test the way the kernel handles networking issues. So behind the scenes, what Pumbaa will do, it will use TC to mess up the network so you can self-inflict errors on your containers and see if you can survive. So how do you DDoS yourself? Well, you run, the easiest way, you run a load test. You run a load test, and then you realize, okay, my application doesn't scale as I expected, so what I'm going to do, I'm going to switch to my Kubernetes cluster, and I'm going to say, okay, scale it to 4 instances. And because, again, this is a reactive system, it works with message-driven architecture, scaling is as simple as this. A request comes in, Kubernetes will just dispatch the message to the right pod, and if the pod is too busy with CPU, it can delegate the message to the other nodes, other pods, other nodes on the network. So now my application has 4 instances. Everything should be working as I expected, and I need to. So DDoS is kind of trivial. Network outages. And this is where we start using Pumbaa. So I can start and copy this command, Pumbaa. As I said, like the slides will be shared, so you don't need to memorize the command because myself I don't know it by heart. So I can create a new window, I can paste it, and I start. You see that things will start getting nasty because, well, this is just network outages, so it's not, you don't really see big issues. You only see that the application itself might get a bit slow, or sometimes the pedal will lose a couple of impulses. But the application is recovering, and you can still play like it's like hours of pleasure, like there's no end. So as you can see, because I'm using a reactive system, this is not really a big deal. But of course, you need to look at your own problem. It's a very simple application. So other alternative to do network outages is to introducing delay, so messages get delayed. So you see that you send a message to an impulse to the client, and then it gets lost for like half a second, and you need to look how it works. A third alternative is to go even more crazy, that you start messing up with the jitter correlation between packets, so you start rearranging the order of TCP packets. So what's happening here is that you're introducing errors on your message, because once the message is bigger than TCP frame and you start messing up with the order, then the content gets reconstructed in the wrong order, so you get you self-injecting errors. So again, you'd see either application crashing or not. So on the last but really important one is when you start introducing server crashes. So this one is more interesting to show, because I can just copy, switch to the terminal, I paste it, and if I go back to here, if things go right, well, I'm probably doing lots of, let me put application. I don't know what's the delay I'm using here. I need to 1 minute to delay. It's probably too much. So let's just say I'm gonna kill every 30 seconds. Well, let's go wild. 50 seconds. So every 15 seconds it should start killing pods. And if my regular expression is correct, well, it's a demo, of course, so things need to, it's a demo, and probably I'm going to stop my plan B also. It doesn't. Okay, so I'm sorry for the demo, it's like failing right now, but what you should expect to see is that this blue circle would start shrinking, and you start seeing that pods would die and respawn itself because Kubernetes is trying to recover. And because you're building the application on top of a reactive system, the application would still work as expected. So for some reason it took forever, and it, 1 minute and 50 seconds. So that's not, for some reason, it's not. So 15 seconds. Oh, come on. So let me just, now after 15 seconds. Terrible. Now, sorry for the demo is not working as expected, but what you should have seen, this is a bit too bad it's not showing up right now, is that this blue circle would start getting orange because the pods are being killed, and Kubernetes would be starting respawning them, and you'd still be able to work with your application. And this is because the JavaScript part would try to reconnect to the next available pod, and your application would still be resilient. So if I go back here, so if everything would be worked as I was planning to, that's what you would be seeing. So, and now that you know how these tools work, and you can investigate yourself. There, it's up to you how to automate this. You can make scripts, you can use automation tools, so they can run continuously, and you see how your system behaves. But remember, it's like the Murphy law, like you really need to minimize the blast radius. So no matter what happens, things will fail. So we need to look into other alternatives, like, okay, what happens if my database goes down? Should I introduce a circuit breaker pattern on my application? Should I have a fallback database or a fallback error message to my end user? You need to think of these things. You need to be creative. So my tips to minimize blast radius is like tip number 1, have a fallback plan, have a plan B. Tip number 2, you should avoid monoliths, because once the monolith goes down, everything goes down. But that's kind of obvious. You should deploy across different regions or even platforms if you can, because then if one region of your cloud goes down, the other one can sustain your business. You should probably use circuit breaker patterns introduced to handle all these failures. And I suggest that you should look into the Awesome Cows Engineering page, where there are lots of articles, tools, examples, and you name it. And finally, like, you should be creative, because you know your problems better than I do and anyone else. So you need to think of these things yourself. So this is what I would like you to take from this talk. So thank you very much for your time. And if you have any questions, please come closer or raise your hand, and I'll try to answer. Thank you. Thank you.